Chemical Nomenclature Part 4, Ionic Compounds, Turning Formulas into Names. An ionic compound is always written with the positive ion first, negative ion second. So when we name an ionic compound, we're going to name the positive ion and name the negative ion, and that will give us the name of the compound. Now remember that ions that are positive can be monatomic. And then we name monatomic positive ions with the element name. So for example, Mg2+ is magnesium ion. Positive ions can also be polyatomic. And the one polyatomic ion that we should look out for is the ammonium ion. Negative monatomic ions can also be named with the element name, but we change the ending to IDE. Now, ions that are negative but polyatomic would have an ite or an ate ending, and there are a few exceptions to that. Now, we had a video, there's a video that we previously looked at where we took a look at how to find ions on this ion sheet. So if you're not familiar with this, you might want to watch that video before you continue with this one. So we're going to talk about how to take ionic compound chemical formulas and turn them into names. And it's important that we do this with two steps. The first thing we're going to do is write out the ion formulas. And then once we verify those are correct, we're going to name those ions. So let's take a look at an example. Let's say we have a compound formula MgO. We could look on our periodic table and see that Mg is in the 2+ column. Now we'll always want to cross-reference and look up here, and you can see Mg isn't listed up here at all. That means Mg does not exist with any other possible charges. So we're just going to call that the magnesium ion. If we look at where O is on the periodic table, we can see that's in the 2- column, and that's indicating that it's a monatomic negative ion. And remember, we use IDE for the ending for that one, for the suffix. So we have Mg2+, O2-. Let's just be sure we have the correct ions for that compound. If we crisscross the 2 and the 2, what happens is we initially get Mg2O2, and then we reduce that down. 2 divided by 2 is 1, and 2 divided by 2 is 1. So it becomes Mg1O1. Well, that's the same as MgO. We don't write those ones in the formula typically. So we do have the correct ions. Let's name those ions. Magnesium oxide. All right, so it can get a little bit more complex, and we should pay attention to some of those complexities. One thing that we have to remember is that we should use Roman numerals when the positive ion has more than one possible charge. Now, we don't ever see this happening for a negative ion, but sometimes this happens for a positive ion. And then we indicate what the positive ion charge is by using a Roman numeral. So we rarely see charges greater than 10 positives. So we should memorize 1 through 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are the Roman numerals 1 through 10. Let's take a look at how that works for an example here for MnO3. This is an ionic compound formula, chemical formula for an ionic compound. Okay, first of all, Mn is in the middle part of the table here. So it's not in a column where we can predict its charge based on its location like we can for these elements or these elements, for example. So what we do is we look on this reference sheet up at the top, and experimentally it has been determined that manganese can actually produce a lot of ion charges. It can produce a 2+, 3+, 4+, 6+, or 7+ ion. Now Mn is manganese, and if you didn't know that, you would look at a periodic table like this one. This is just in the back of a chemistry book. And you can see that manganese is listed here as Mn. So you might want to have a periodic table with element names on it so that you can look up the names of elements if you need to. All right, so we have manganese with all these possible charges. And the other part of this compound is O. Now you'll remember we just looked at that O is 2- in a previous example. So we have some type of a manganese oxide here. Let's list all of these charges that are possible for manganese. And also let's list the O with its 2- charge, because that's going to be important to us. All right, so because there's a 3 there, you might be tempted to use the 3+. Now that's not going to work, and let's take a look at why. If we have Mn3+ and O2- and we crisscross the 3 and the 2, remember the procedure there is we move this number down here and we move this number down there. We drop the plus and minus signs because compounds are always neutral, so the pluses and minuses always balance. We would get Mn2O3. Well, that's not going to reduce at all, and we certainly don't have Mn2O3 up here, so Mn3+ can't be the correct positive charge for manganese. Let's try another possibility. Let's try 6+. If we crisscross Mn6+ and O2-, notice the 6 goes there and the 2 goes there, and we get Mn2O6. Now Mn2O6 are both divisible by 2. 2 divided by 2 is 1. 6 divided by 2 is 3. Hey, that's the right formula that we have. So Mn6+ is going to crisscross with O2- and give us that formula. So we call this manganese for Mn, Roman numeral 6, because we use the 6+ oxide. Again, IDE ending when the negative part is monatomic. And on this ion sheet, there's a little reminder there that these are all IDE ions that we have here. So we just name the positive ion, name the negative ion. But it's important to use a Roman numeral. Now you might be tempted at some point to just call that manganese 3 because of the 3 down there, but be careful. The Roman numeral is always indicating the positive charge that's being used, not the subscript that's down at the bottom. Because sometimes, like in this example, reducing happens. So it's important to look at all the positive charges and the negative charge and consider how the reducing might work. At the very minimum, you should write out these ions, because while you might be able to do a little bit of this work in red in your head, it's a lot to remember the ions and consider these possibilities at the same time in trying to determine what the correct name is going to be. So when we write the ion formulas, the first step in our 2-step process, we want to make sure we write all the ion formulas. That's going to give us a chance to do 2 things. Number 1, it's going to give us a visual reminder that we have to use Roman numerals. And number 2, it's going to allow us to do a visual inspection, so you don't have to keep track of all those ion charges in your head and do all the crisscrossing in your head. So once we have those ions written down and we determine which ones are the correct ions, again, we just name the ions. That's our second step. That gives us the name of the compound that is represented by the formula. Let's consider PtO2. Now Pt is some platinum compound, right? Pt is platinum. And if we look on the periodic table, you see platinum's right here. There's no charge that we could predict for platinum based on its location on the table. But we do know from experiment, and that's written down here, the results, that Pt can form a 2+ or a 4+ ion charge. So we list that down, 2+ or 4+. And then we've been using O here for a while. O is in the 2- column. So we have some type of a platinum oxide. Now if we use 2+ and 2- and crisscross, we'll initially get Pt2O2, but that reduces down to PtO, right? We'd have 1 Pt and 1 O, and one of each would not match PtO2. So that's not a correct formula. That 2+ can't be the correct ion. Let's consider if we use the 4+. So here we have Pt4+ and O2- crisscrossing. The 4 goes there and the 2 goes there. And we initially get Pt2O4. Now that reduces down. We can divide 2 and 4 both by 2. 2 divided by 2 is 1. 4 divided by 2 is 2. So Pt1O2 matches that formula there. So this is actually platinum 4 oxide. And if we get PtO, we've used platinum 2+. This is platinum 2 oxide. So what I think some people will do is they'll consider the positive ions, consider the number at the bottom, and say, well, since that's a 2 on the bottom, must have been a 2+ that crisscrossed. Well, sometimes reducing happens. Like in this example, reducing happens. So it's important to write out all of the ions. So another complication can be that we have polyatomic ions. Remember that we always put the positive ion first, negative ion second. And it's important that you start to recognize polyatomic ions. And this just comes with drill and practice. I think it's very much like reading. You just begin to learn to recognize words. So as you're reading, you don't really sound out the word the. You don't say the. You just know that when you see THE, it's the. It's a sight recognition word. So after a while, that will happen with ions. Remember that we said that the one positive polyatomic ion we have to keep our eyes out for is NH4 1+. So when we see a compound like this, and you're wondering where is the positive part and where's the negative part, like what's the dividing line? Well, keep your eyes out for that NH4 1+. We can see we divide that compound right there. So we have NH4 1+, and that means NO3 must be the minus charge there. And we could verify that. We could look on our ion sheet where the positive or where the negative polyatomic ions are, and we can see that NO3 is one of the negative polyatomic ions listed. So if we use NH4 1+, and you don't have to memorize that, you can just look that up here on the sheet, right? And NO3 1-, well, we could crisscross those. One goes there and one goes there, and we'd get one NH4 and one NO3. Now, if you want to write the ones there, you have to put the parentheses around the ion formulas. But we really don't need the ones, and we don't need the parentheses, so we just write it this way without parentheses, NH4NO3. So this is called the ammonium ion. We call that ammonium, and that's called, well, we'd look that up here, right? Ammonium ion and nitrate. So this is called ammonium nitrate. As you get more practice, you'll begin to recognize polyatomic ions a little bit more easily. But until then, you just have to make sure that you find the correct ions by looking on the ion sheet. Now, it's important to remember that with positive ion first, negative ion second, ammonium ion, NH4 1+, is the only positive polyatomic ion that we will use, at least in first year chemistry. And that's so that we can more easily divide up the compound into the positive and negative part. So for example, NH4Cl would divide up after the NH4. So we'd have NH4 1+. Once again, that's on the ion sheet here, ammonium ion. And Cl would be in the 1- column. So Cl 1-. If we crisscross the ones, we would get that. Right? NH4 in parentheses taken once, Cl1. Remember that if we put it in parentheses, we say it's taken so many times with the number on the outside. So NH4 taken once, Cl1. We don't need the ones, so that means we don't need the parentheses. It's typically written like this. And the name of that compound would be ammonium for the ammonium ion, chloride for the chloride ion. It's ammonium chloride. All right, so here we have CaCrO4. Now we can divide that up after the Ca because if NH4 is the only positive polyatomic ion we have, that means that if a compound starts with anything other than NH4, we can divide it up after the first element. Now you'll remember that elements on the periodic table each have their own capital letter. So we divide it up after that first element. All right, so here we have Ca and CrO4. Ca is right here, it's in the 2+ column. And CrO4, well, that's got to be a negative polyatomic ion. We can find it in here. In fact, we can see it's right there, CrO4. It's got a 2- charge. So here we see Ca2+ and CrO4 2- are the ions. When we crisscross that, we can see that we have Ca2+, CrO4 2-. The 2's crisscross. We initially get 2 and 2, and they both reduce down. 2 divided by 2 is 1, 2 divided by 2 is 1. Now, we could write it this way with, a 1 and a 1, but we don't really need to do that, and that means we don't need the parentheses, so we just write it this way. That's calcium chromate. Here's another example. Na2SO4. We're going to divide it up after the Na. So that's Na, which is an ion or an element that's in the 1+ column. So Na1+ would be our ion. And SO4, and we can look on the ion sheet and see that SO4 is, well, there it is. It's It's 2 minus. So we have Na1 plus and SO4 2 minus. If we put the 2 there and the 1 there, right, the 2 there and the 1 there, we would get Na2 and then SO4 taken once, right? That 1 would go there. And if we wanted to, we could write the parentheses and the 1 there. People typically don't do that. So they drop the 1 and they drop the parentheses, and we just write it like that, Na2SO4. So that's called the sodium ion. That's called the sulfate ion. Sodium sulfate. Sulfate. Now you might say, how do you know Na is sodium? Well, once again, that's when you would have a periodic table with element names on it, like this one, and you could see that here's Na, it's called sodium. So you might remember that when you learned to read, it was a little frustrating and you had to use the dictionary a lot. So this is kind of the same thing. When you're looking for ions, until you become more familiar with ions, you're going to have to, take your time and find the ions on the sheet. That's going to take a little bit, and you might have to look up element names on the periodic table too. Just takes a little bit of drill and practice. All right, so in compound formulas, polyatomic ions are in parentheses if they have a subscript that we crisscross to the outside. And if you remember that, that means that it can maybe simplify some weird examples, like, let's take a look at these. In this left-hand example, we have AuClO3. All right, so Au is right here. It's in the middle part of the periodic table, so we can't determine its charge from there. So let's look up here and see if we have some experimental results for Au, and we do. Au could be 1 plus or 3 plus. Now Au is the element gold. So we're going to have gold Roman numeral 1 or gold Roman numeral 3 in this compound. So it's going to turn out to be 1 plus, the 1 that'll work. But let's consider what the negative ions might be. Now ClO ions are all found here. If you watch the video where we talked about this ion sheet and where to find ions, these are called halogen oxides. And they're ClO1 minus hypochlorite, ClO2 1 minus chlorite, ClO3 1 minus is chlorate, and ClO4 1 minus perchlorate. Now, all of these halogens are the group 17 elements here. The common ones, fluorine, chlorine, bromine, and iodine, the ones that are not radioactive, all behave the same way. So we're just going to take a look at it for chlorine because that's what we have here, a chlorine oxide or a halogen oxide that's made of chlorine ion. So do we have this one or this one or this one or this one? Well, it looks like we have ClO3 1 minus. Looks like we have chlorate. So we're going to have some type of a gold chlorate. Is it gold 1 crisscrossing Roman numeral 1, or is it gold 3 crisscrossing, crisscrossing the 1 plus charge Roman numeral 1, or gold 3 Roman numeral 3 for the 3 plus charge? If we put the 1 there and we use 1, this one will go here and this one would go there, and we would get Au1 ClO3 taken once. Well, if we don't write the ones and we don't write the parentheses, that's what we have there. So this compound would be gold 1 chlorate. So the first step is to write the ions and then verify that you have the correct ions. The second step is to write the name of the compound. Let's take a look at another example here where we have Au, but now ClO is taken 3 times. Again, consider that language that we use there, ClO taken 3 times. So we know that Au could be 1 plus or 3 plus. And it turns out that ClO1 minus is another possible ion that exists. That's called hypochlorite. Well, that's the ion we have here. Now, if we crisscross Au3 plus and ClO1 minus, the 3 goes there and the 1 goes there, and we get Au taken once, ClO3 taken, or I'm sorry, ClO taken 3 times. So that is the formula that we have here. So Au3 plus is called gold 3, and ClO1 minus is called hypochlorite. So we have gold 3 hypochlorite. So the name of the game here is be careful when you select your ions. Now, these are awful tricky examples. And you know, you might be a really good reader, but you might run across a word that you're unfamiliar with, and it may be that you have to pull out a dictionary sometimes. So I think in reality, we got to be, you know, aware of the fact that, you know, some chemists are really, really good at nomenclature, and they're very good at site recognition, and they might be able to look at this and say, well, this is, you know, gold 1 chlorate, and that's gold 3 hypochlorite right off the top of their head. But realistically, all chemicals come with a label on the bottle, and the label will have 2 things on it. It'll have the name, and it'll have the formula. So let's not forget that. You can always look up words in a dictionary, whether you don't know the definitions or if you don't know the spelling. And you can always look at the label on a chemical bottle and look at the formula or look at the name. So why are we doing this nomenclature? Well, you wouldn't want to have to read and use the dictionary every single time that you were looking at a word. So we need to have some kind of a vocabulary here where we can do some chemistry.